Hello friends, in this video we are going to see the topic synchronization tools. Under that, critical section problem, synchronization of hardware, under semaphore in the subject CS3451 Introduction to Operating Systems. This is Satish Pandian, Assistant Professor, Department of CSE, Government College of Engineering, Bodina, Ekanur. First, we will see why we are going for process synchronization or what is the need of synchronization. So, see the definition. When several processes access and manipulate the same data concurrently, the result may be inaccurate. Just I will tell an example. In a class, we have 50 students. We are saying an announcement in the nearby, that is the next room. There is a cake. Like that, we are telling an announcement. So you people go and take a cake. So what these students will do, immediately all the 50 students will rush up and try to take the cakes. So that will result in inaccurate. So in this case, we need a synchronization. Similarly, if any common data is there, when multiple processes are allowed to access the common data at the same time, the result may be inaccurate. So in that situation, we need process synchronization. Related to synchronization, we have another definition called a race condition. It's like a running race. Suppose there is a 100-meter race. 6 to 8 participants are participating in the race. So after the whistle, they have started running. So who will come first? The first prize goes to who will come in first. So the output or the outcome is always depends on the order. Same thing here also. When multiple or several processes access and manipulate the same data concurrently, the outcome is based on the particular order in which the process access the common data. So in which order the process access the data, in that based on the order only, the outcome of the result will be that. That is called a race condition. So now we are going to see the topic critical section problem. Okay. So introduction. Here we are taking n number of processes. Each process has a segment of code called critical section. For example, for simple understanding, take two processes, P1 and P2. So P1 we have just 10 lines, P2 we have 10 lines, just for example. In P1, the fifth line is going to access some common data, just for example. Similarly, in P2, the seventh line is going to access the common data. So the fifth line of P1 and the seventh line of P2 is called a critical section because in this area only, the process is going to access the common data or resource. Okay. So critical section is nothing but it's a part of a process or a part of a program. Inside that, the process going to access the common data. Here, what is the problem means? When we allow both the process, that is a P1's fifth statement and a P2's seventh statement are executed at the same time, what will happen? Both the process will access the common data at the same time. The result may be inaccurate. So we need to provide synchronization. So this common execution we need to restrict. Okay, so that is this problem, critical section problem. So that is given here. When one process executing in its critical section, no other process is to be allowed to execute in its critical section. That means if we allow P1 to execute its fifth statement to access the common data, at the same time, process P2's seventh statement cannot be allowed. That is the statement. So automatically, the execution of critical sections by the process are mutually exclusive in time. That means we have to allow only one process at a time to execute their critical section. So critical section problem, the mutual exclusion principle we need to follow. Here, that's a simple solution how to solve that critical section problem using a simple coding. There's a simple do while loop. It should be implemented in every process. So when every process wants to enter the critical section, this is the critical section. What is critical section? Previous slide we seen. Inside this, the process going to access the common data. Okay. So whenever a process going to access the common data, it has to get permission in the entry section. So initially we have entry section, process gets permission. When the process is permitted, if there is a condition that if no other process executing their critical sections, or if none of the process executing their critical section, then one processes load in the entry section to enter into critical section. Then in the critical section, the process can access the common data. Once the access is over, it can come to exit section. Once the process comes to exit section, then it can be allowed some other process to enter into critical section. Normally, a solution. This is a solution for a critical section problem. General solution to critical section problem should satisfy these three conditions: mutual exclusion, progress, bounded waiting. Okay. So here, just a simple solution is given for two processes. That two processes are taken as P0 and P1. For these two processes, how the critical section problem is solved. Here, we are going to use three algorithms. The first algorithm uses a variable called a turn. Initially, turn is equal to 0. We can interchange the values. Either it may be 0 or 1. Okay, that can be represented as I or J. When turn is equal to I, the process PI is allowed to enter into critical section. Since we have two processes, one is considered as PI, another one is taken as PJ. Whenever the turn variable values I, PI is allowed to enter into critical section. Whenever turn is equal to J, PJ can be allowed into critical section. So this is a simple coding for that. This is the algorithm 2 to implement a critical section problem for two processes. So previous algorithm, we used a turn variable. If turn is equal to I, Pi is allowed to enter into critical section. Similarly, instead of a single variable, here we are using an array. It's an Boolean array. Array name is flag of 2. That means we have two variables, flag of 0 and a flag of 1. Whenever flag of I, that is flag of 1 is true, the first process, Pi or P1 is allowed to enter into critical section. Whenever flag of J is true, the second process is allowed to enter into critical section. So both are almost same algorithm 1 and 2. In algorithm 1, single variable is used. Here, an array is used. And then algorithm 3, both are combined. The Boolean variable, flag of 2 is used, and then an integer variable turn is used. For first process, flag of I should be true, then turn is equal to I. If both the conditions are true, first process allowed to enter into critical section. Otherwise, the second process allowed to enter into critical section. So this algorithm 3 is called Peterson's solution. So previous three algorithms for a two process. This is an algorithm for a multiple process solution. Consider we have many number of processes. How the critical section problem is solved for that number of n number of processes. That solution is called a Bakary algorithm. The corresponding algorithm is called a Bakary algorithm because the system is normally is similar to what in foreign countries Bakaries are following. Okay. So in Bakary, when a customer is entering, they receives a number like outside hospitals we are doing no. Whenever we are entering into hospital, we are getting a token. The patient which has lowest token will meet the doctor next. Same thing. Customers receives the token after entering in the Bakary. Which customer has the lowest number will be served next. Same concept is followed here. This algorithm is called a Bakary algorithm. Okay. So this is a solution or this is the Bakary algorithm which gives the solution for a critical section problem for n number of processes. So with that, that topic is over. The next topic is synchronization hardware. So like a software, using some hardware instructions also, we can able to provide process synchronization. So these are some instructions, test and set and stop. So before that, a small definition is that memory barriers. So normally a memory model will be two kind, strongly ordered or weakly ordered. Strongly ordered is nothing but whenever there is a memory modification, it is which is done by one processor, that will be visible to all other processor during multi-processor environment. But in weakly ordered, that reflection will not be immediately seen by other processors. Okay. So whenever we are doing or we are making some memory change or memory modification, which is done by a single process, others should know that memory barriers or memory fences are used. Okay. So what it will do, memory barrier instruction is performed. Whenever we are executing a memory barrier instruction, it ensures that all loads and the stores are completed before any subsequent load or store operations are performed. So whatever already pending everything should be completed. All loads and store instructions. That is the use of memory barrier. Okay. So here, a simple example is given. A thread like two process, thread one and thread two. In both sides, we are using memory barrier. Here, we are using memory barrier. What it will do, it will complete all load and store instructions. So here, see the output. This is thread one. Here, we are printing the output as a value of x. Without a barrier, if you execute the coding, the print x will give the output 0. But with the barrier, if you execute a barrier, what normally will do, it will complete all load and store. So here we have a store instruction. The value 100 is stored in the variable x. So it will be executed. Then while printing x value, we are getting output is 100. That is with the memory barrier. This is a hardware instruction for synchronization, test and set. So first we are going to test the variable and we are setting. That is called a test and set. Okay, it is done by this coding. So this is a do while loop. Here while test and set lock. So variable lock is given. If this lock is initially false, it will be set as true. If it is true, it will be changed as false. That's the thing. Okay. So we are check while we are calling a test and set instruction. So automatically it will go to this function test and set. The log value is passed here. Here we are changing. Initially it will be false. Here we are making it as true. When it is true, the process can enter into critical section. Okay. After a critical section, the log can be changed as false. Okay. This is how synchronization is achieved using test and set. Initial value of log is false. Okay. So here, while coming to this while loop, the log value is false. We are executing or we are calling the test and set log method. This method will be called. So target, the log value will be there. So target is initially false. Then we are making the target as true. After making true, the process enters into critical section. Once it is over, again the log will be false. Okay. Similar to log, there is another hardware instruction is that swap. Okay. So here again log is used, which is initially false. Okay. So this is swap method. This is a do while loop for a process synchronization. Here we have another variable inside the loop, key. So key value is true. Here lock is already initialized as false. So two variables we are using. Key is true, lock is false. That two values we are interchanging. So see that while key is equal to true. So key is until key is here actually key is equal to true. This is satisfied. So we are calling swap lock comma key. So lock is initially false. Key is true. This swap method is called. Here both value we are interchanging. After interchanging, we are getting lock is true, key is false. Now lock is true, so process can allow to enter into critical section to access the common data. After that, the lock again to be considered as false. Okay. So this is using swap instruction how synchronization is achieved. Okay. So these two instructions, test and set, swap, are hardware instructions which provide a process synchronization. The next topic is semaphore. Again, it's a synchronization tool used for the process synchronization. Here, how it works means normally semaphore is a variable. It's an integer variable actually. Normal values we have in the semaphore variable. It is represented as yes. This variable will access two common operations, wait and signal. They are termed as P and V. It is a definition of wait. This is definition of signal. So wait. Yes, yes is nothing but semaphore variable. If the variable is less than or equal to 0, no operation is performed. Otherwise, it will be decremented. Okay. Here, signal, just we have to increment the semaphore variable value. In signal, nothing we are doing. Whenever there is a signal operation, the value will be incremented. During wait operation, value will be checked. If it is less than or equal to 0, no operation. Suppose if it is greater than 0, process can be allowed to enter into critical section. During that time, it will be decremented. So there are two common uses of a semaphore. We can solve critical section problem, and this is a second use we will see. So the first use is end process critical section problem can be solved using semaphore. So this is the coding for solving critical section problem using semaphore. Here, what variable, semaphore variable we are using, mutex. Initially, it is initialized as 1. So this is a do while loop. Normally, semaphore can access two operations, wait and signal. So here wait, here signal. So in wait, we are giving the semaphore variable value. Initially, it is 1. So according to this definition, if it is less than or equal to 0, the process will wait. But here it is positive. That means the process can be allowed to enter into critical section. While allowing critical section, this value will be decremented. Now it will be 0. At the same time, suppose consider some other process is trying to enter into critical section. That process will execute the same coding, weight of mutex. Now the mutex is 0. The second process will not be allowed to enter into critical section until the completion of first process. So consider first process completes the critical section and come out of here. It will execute a signal of mutex. Signal what we are doing, just we are incrementing the variable. So here the mutex will be incremented. Now it is again from 0 to 1. Okay. So now the mutex becomes 1. Again the second process tries the weight of mutex, it can be allowed because first process already completes the execution of critical section. So like that, using simple semaphore concept, n process critical section problem can be solved. This is another use of semaphore. Here what we need to do means process P1 consider having a statement S1, process P2 having a statement S2. Our task is S1 to be executed before S2. So two processes are executed parallelly or concurrently. Always S2 should be executed after S1. That is the S1 executed first, then S2. So this order we need to maintain. For that also we can use semaphore. So here semaphore variable what we are using is a sync, which is initially given the value 0. Okay. So the semaphore can use, we have just studied wait and signal operation. These two operations can be used here. Wait operation is given in process P2 above the statement S2. Similarly, signal operation is given in the process P1 below the statement S1. If you give like this, then automatically that order will be preserved. That is, S1 will be executed before S2. So just to check it, the sync value is initially 0. So process P2 suppose executes quickly, it comes to the statement weight of sync. So sync is already 0. If it is less than or equal to 0, no operation. So process P2 will be blocked until the sync becomes a positive. When it becomes positive, whenever the process P1 executes a signal of sync, then only it will be incremented. When it will be incremented after S1. So process P1 executes S1, then executes signal of sync. Now signal sync becomes 1. Whenever sync becomes 1, then P2 can execute a wait of sync followed by S2. So after S1 only, S2 is executed. So this order of, for this kind of order of execution, we can use a semaphore. That is a second use to execute process in some particular order. Okay. So the general implementation of semaphore leads to busy waiting. What is busy waiting means? Consider this. Here we have a while loop. Now while s less than or equal to 0. S is semaphore. Continuously a process checks the value of semaphore, whether it is positive or not. Okay. Whenever it is positive, then only process can enter into critical section. Otherwise, no operation. So it is given under while loop. So continuously a process checks the semaphore value. So that is called a busy waiting. Due to busy waiting, many CPU cycles are wasted. So spin lock occurs. This is a drawback. To avoid this drawback, a new modification of semaphore is given using a C language coding. This is a structure. Okay. Whenever a process wants to wait, it will not continuously check the semaphore variable. Instead of that, that process will be added in the list. This is a list. Okay. Here, what are the processes that are waiting to or that are ready to enter into critical section? They will be placed in this list. It's like a waiting queue. In this, it will be placed. And then in the semaphore operation, whenever a process completes the semaphore, from this list, one process can be taken. There is a remove a process from this list and a wake up and start to execute that process. Okay. So this is a new implementation. Here, busy waiting drawback will be eliminated. This is another definition related to semaphore, deadlock and starvation. So deadlock, both are waiting for a long time, indefinite waiting. That is called a deadlock state. A simple example is given. Here two semaphore variables are used, S and Q. Okay. So weight of S, consider initially both S and Q are value 1. Okay. So after a weight of S, the P1 can be allowed to enter into next statement and S will be decremented. So S becomes 0. Similarly, P2 executes weight of Q. So P1 goes to next statement and the Q will be decremented as 0. Now come here, weight of Q. Already here, the Q values changed as 0. So this weight of Q will not be executed. So P0 will be blocked. Similarly here, weight of S is here changed as 0. So P1 while coming to execute a weight of S, it will not be executed because already S is 0. So both processes will wait for long time until these two operations, signal of S and the signal of Q. But these two never executes because both are blocked in the second line itself. These two processes will wait for a long time. That long waiting will lead to deadlock. So there is another definition related to semaphore, which is a binary semaphore. Normally semaphore is an integer variable, any value we can store. But in binary semaphore, it can store the binary values either 0 or 1. So we can create a binary semaphore like this. Binary semaphore S1, S2. So here both semaphore binary semaphore variables, it can contain either the value 0 or 1. So this video, we discussed why we need a process synchronization and a critical section problem, how it is solved, and the hardware instructions for process synchronization and semaphore. Thank you.